And we obtained what is called the matrix of linear transformation with respect to a basis. We also have observed that if we change the basis, the matrix changes, and even if you retain the basis as set-wise the same, but if you change the order of the elements, then also the matrix may change. Now, thing is, what could be the relationship when we change the basis? This is what we want to now study. So, let me then come to what is various examples we had already seen. Now, let us uh, obtain a few simple properties for the matrices. So henceforth, when we say with respect to a basis, we shall also specify the order of the basis elements. And in that case, we shall call it an ordered basis. So an ordered basis means so let us say V over F would be a vector space of dimension n, and a basis say B, V1, V2, say Vn, or V over F is called an ordered basis. If the order of elements, order in which the elements of B are stated, specified. So B and B and B prime, let us say B prime is some other order. So say this is V1 sigma and V2 sigma, and say Vn sigma. Are for are same ordered basis. If and only if sigma is identity permutation, Sn is the identity permutation. Because if sigma is identity permutation, in that case, the order of these elements will be retained. And if it is not identity permutation, then order will be definitely changed. Although set-wise both are same. So although, however, set wise both are equal. So henceforth we shall specify the order also of the basis vectors. And if we consider T as a linear transformation on such a vector space, then the matrix of T with respect to an ordered basis B will be denoted by TB. So henceforth TB will denote the matrix of T with respect to an ordered basis B for the vector space B over F. So we want to see that if we change the ordered basis, that means the elements themselves may change, or even if set wise it is same, the order of elements may not be same. And some properties of the matrices now we want to obtain, as we have been knowing matrices since the school days. So at that time these properties were stated as that these are the assumptions, but now it's the time that we must prove that the assumptions made at that time are actually real, that they really make sense. All right, so let us take a B be a finite dimensional vector space, and so let us take dimension of V F B N, right? And B, let us take V1, V2, Vn be an ordered basis for V over F. All right, let us say this AFB is to denote the vector space, in fact, the algebra of all linear transformations on V. So suppose we have here say linear transformation T and S with two linear transformations. So this is what? This is the algebra of linear transformations on V. We know that this is an associative algebra with identity over F, the vector space, as well as a ring. Now define a few things that we know. So recall that two linear transformations, so they are after all mappings. So they are the same if and only if Vs and Vt are same. So recall the two linear transformations or two mappings in fact are same if and only if Vs and Vt are same for every V in V. And as we know that every linear transformation is completely determined by the images of basis vectors. So this is also if and only if each Vi under S is same as this for every I 1 to n where VI's are the basis vectors. Now, if that is the case, what do we get here? So, if S and T are equal, therefore, the matrix of S with respect to the ordered basis B and the matrix of T with respect to the ordered basis B will be equal. Because that's what you write. What you write to write the SB, that you write VIS as a unique linear combination of VIS in terms of the vectors VI. And the same for VIT is done. And since each VIS and VIT are equal, the linear combinations are equal, and that will give, because VI's are the basis vectors, that each coefficient is equal. Since when you write this SB, so VI under S as the linear combination. So suppose the matrix of this is say alpha ij. So this is say alpha ij, and this is Vj, J1 to N. So that is the matrix of this is alpha ij. So that makes the matrix of S with respect to the basis B is the matrix whose ijth entry is alpha ij, n by n. Now, since VIS is same as VIT, so VIT is also same as that. So VIT is same as VIS, is same as alpha ij Vj, j is equal to 1 to n. That means what? Matrix of T is here with respect to the ordered basis B is also alpha ij. Each entry are equal. So the matrices will be equal, and this is if and only if. If you take the matrix of S is this alpha ij, and the matrix of T also will turn out to be alpha ij. Conversely, if you take the matrix of S as alpha ij, matrix of T as beta ij, and these two being equal means each alpha ij is equal to beta ij, correspondingly you get this result. So this is the first thing that we obtain. The two matrices are equal if and only if. So two matrices are equal if and only if each entry is equal. So two matrices here are equal. So alpha ij equal to beta ij, n by n, n by n. If and only if each alpha ij is equal to beta ij. So this is one property of the two matrices being equal. Yes. Okay. All right. Next, what would be the matrix of the sum of two linear transformations? So recall that if S is a linear transformation, so S is a mapping V to V, and T is also a mapping V to V, and V goes to Vs, and this here V goes to Vt. Then recall S plus T is defined as the mapping V to V, such that V goes to V under S plus T, and this way is defined that Vs plus Vt for every vector V in And we know that this S plus T is also a linear transformation. So we know that if S and T are in AF, so S P in AFV and alpha in F, then we know already that this is an alpha. Therefore, S plus T, ST, TS, all such alpha S, alpha T, all of them like that, they are in AF or alpha beta. So once they are linear transformations, so we want to know the matrices of these linear transformations. So we want to know what is the matrix. So to know matrix of the linear transformation S plus T with respect to this ordered basis B. All right, so suppose in terms of, so let us take SB, so we say alpha ij n by n, and the matrix of T with respect to the ordered basis B says beta ij n by n. Then we want to know what is the matrix of S plus T with respect to this ordered basis B. So if these are the matrices, so what does it mean? So we know that VIS is the linear combination of these basis vectors Vj's, J1 to n. And we also know that VIT is the linear combination beta ij, and this is Vj, J1 to n, and this is for every I 1, 2 up to n max. So what we have here is that we can see that Vi under S plus T, which is VIS plus VIT. So this naturally you can see that this is the linear combination alpha ij plus beta ij Vj J1 to n for every I 1 to n. So what does it give me? This gives me that the matrix of S plus T with respect to this ordered basis B is the matrix of S, this entry. This is, what is the ijth entry? Alpha ij plus beta ij. So this is the matrix. So arbitrary element here will be what? So the arbitrary element here of this is alpha ij plus beta ij n by n. So this is the matrix here of this. So the matrix of this S plus T is the matrix whose ijth entry is this alpha ij plus beta ij. You can also see that similarly for every alpha in F, so alpha T is a linear transformation, and alpha T is defined as V to V. V goes to alpha T under V is alpha VT, if you remember. So the matrix of alpha t, if I have to write matrix of alpha t with respect to the B, if I want to write its arbitrary element, then what do I have to see? What is the effect of the alpha t linear transformation on each basis vector, say Vi. Now t is a linear transformation, so this is same as VIT. VIT is the linear combination, unique linear combination alpha ij Vj. J is equal to 1 to n. This is same as alpha ij Vj. J1 to n. So what is the, if I have to write the ij entry of this, then this is alpha ij. Where the matrix of T is alpha ij. So you can see that the matrix of alpha T with respect to the ordered basis B has the entries where each entry of the matrix of T with respect to the ordered basis B is multiplied by alpha throughout. One more thing, let us take now the product here. So the product needs the composition of mappings. Next is this. So this is also V to V. V goes to V under ST. How did we define Vs and then we took T? Now we want to know, so to know again here the matrix of ST with respect to the ordered basis say P. So what do I have to know? So suppose this is, let us say this is say gamma ij n by n, suppose this. So to know gamma ij, what I have to know is that what is Vi under St. So Vi under St is Vi under S and then T. Now, this is a linear combination of the basis vectors. And this is alpha here ij, let us say k1 to Vk and T this. Now this is same as the linear combination k is equal to 1 to n alpha ik Vkt. Now Vkt is the linear combination. The matrix here, let us assume that this is say beta. The matrix of S and T. So the matrix of S and T, let's say the matrix of S with respect to T is alpha ij, and the matrix of T with respect to the basis B, let us say ij. N by n, this is also n by n. So suppose this is the case. So Vkt, therefore, we know because the matrix is beta ij. So this is k is equal to 1 to n alpha ik. Now Vkt. So Vkt will be here a linear combination of the basis vectors. So let us say this is beta k and this is j and this is Vj and j will be 1 to n. So this is same as, therefore, k1 to n and this J is also 1 to n, and the coefficient here is alpha ik beta kj, and since both take values here, so you can interchange also with sum. So this is alpha ik beta kj, and this is the coefficient here, so you have bj, and you can interchange because of this, so you can rewrite therefore that this is here k and this is here j. So this is here is your j and this is here k. So this is the coefficient therefore of Vj. The coefficient, so if you write this as, so this is say j 1 to n, and this is corresponding to I, so this is gamma I j Vj, where what is gamma ij? Gamma ij is summation over k 1 to n alpha ik and beta k j, and this is for every I and j from 1 to n. So the matrix of the composition ST, product of linear transformation ST with respect to the order ST is gamma ij, the ijth entry, and the ijth entry is here summation alpha ik beta kj, k is 1 to n. So we now know therefore the matrix now of composition. Once we have this composition, so you can also know the matrix of say STU, if U is another linear transformation. And since the composition of mappings is associated, so that both will give you that the matrix of STU and the matrix of STU are same. So this is for you to observe. Now what we have seen already here, and these observations can help us now if we want to look at the set just of matrices, then what do we have? So these properties of the linear transformations can be seen helping us in framing the properties of the matrices. Okay, so denote now, let us say this M, N, F. So this is to denote the set of all matrices of order n by n. Say entries alpha ij coming from the field, let us say F. Then what we had already seen because of the properties, so define now. At the moment, this is the set, and we are defining a few things. Number one, for two matrices, let us say AB, or the two matrices, let us say A, alpha ij, n by n, B, say beta ij, and say n by n, and let us say alpha in F. The following. So these two A, B are in M and F, and alpha in F. So define for these the following. Number one. The matrix A is equal to B if and only if alpha ij is equal to beta ij for every I and j 1 to n. That means alpha 1 is same as beta 1 and so on and so forth. Then we say the matrix A is same as matrix B. Conversely, if A is equal to B, what do we mean here is that every entry is equal. Number two, the sum of this A plus B that is the sum of these two matrices is defined by the matrix whose ijth entry is beta ij. Remember that when we write like this, means the entry which on the intersection of ith row and jth column is this. So this is gamma ij, where gamma ij is what? Alpha ij plus beta ij for every I j from 1 to n. So for every I and j 1 to n. The third thing, let us say, is alpha A. Alpha A is to denote alpha, the matrix alpha ij, and to denote the matrix alpha ij n by n. That means the matrix whose every entry is multiplied by alpha. The fourth thing that is defined is the product AB. The product AB is the matrix, product of these two matrices, n by n, alpha ij, ij is the matrix, say, gamma ij by n, where the entry gamma ij is what? As just now we have seen. So this is k1 n alpha kj, no, sorry, alpha ik. So this is alpha ik, beta kj. Again, for every ij 1 to n. If you define like this, then we can also see a few other things. What is the zero matrix means, or the null matrix means all entries are zero. And so you can also define the zero matrix. So this zero matrix is the 0 and n. And the sixth thing that you want to define this I matrix here, whose entries are 1, 0, 0, 0, 0, 1, 0, 0, 0, 1. And so the entries on the diagonal are 1, 1. So this we also can be used to define alpha I. You can see here. So if A is identity, in that case alpha I is here alpha, and every entry because is alpha I is 1. So alpha, alpha, alpha on the diagonal, and therefore this will give you that alpha I is the matrix alpha and then 0, 0, 0, alpha, 0, 0, 0, and like this 0, 0, alpha by n and by n. This is called scalar. Scalar matrix. So various names are given depending on that. This is called identity matrix, called scalar matrix, and it is diagonal entries are lambda 1, lambda 2, lambda n, and all other entries are 0. In that case, this is called a diagonal matrix. Anyway, so define these for any two elements A, B, when F, every scalar alpha in F, the equality, the sum, scalar multiplication, and multiplication. So what it remains is to be seen what algebraic structure M and F may have. So this I leave for you to see that this becomes associative algebra with identity. The identity means with respect to multiplication, the identity matrix. Now that is all. So then if you find like this, then M and F associative algebra with identity, and as a vector space it is over F. Moreover, since this is a vector space, you can also see one interesting thing that further if Eij is to denote the matrix where all integers are 0 except the entries Eij. So this is the matrix, let us say with Eij n by n is such that Eij is delta. No. This is Kronecker delta. That means so. This has nothing to do with Kronecker delta. Eij is 1, but this is not for fixed one. Eij is write in words that is better. Is an n by n matrix for a fixed ij, whose ijth entry is 1 and all other entries are 0. So even 1 is basically here 1, 0, 0, 0, 0, and even 2 is 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, like. So if you take this, then this set of all such matrices is a basis for this algebra M and F over F. And thus the dimension of the vector space M and F over F is n squared, because these are the matrices n squared in numbers. And also recall that the algebra AFV is also an associative algebra over F of dimension n squared. Is a dimension n squared. So we have two associative algebras with identity. This is also with identity. And both are of the same dimensions. What we know is that any two vector spaces of the same dimension over a field F are isomorphic. What do we get here is that these two are isomorphic. This theorem says interesting thing. So what does this theorem says is that AFV isomorphic onto MNF, where what is n? Dimension of V over F and is finite. And one such isomorphism can be seen is the mapping that sends, so let us take AFV to this M and F, Every linear transformation goes to the mapping, sends this to matrix of this. Can be obtained using an ordered basis, say B or V over F S. So this is an isomorphism. This is an algebra isomorphism. That is, it preserves sum, scalar multiplication, and the product, number one. So it preserves the sum means S plus T respect to this is this. This we had already seen. Alpha S. Third thing is ST B. All these properties we had already verified that they hold. So this theorem is actually proved that this is an isomorphism, and this isomorphism is one to one also, that can be seen using the property of the basis vectors, and is obviously onto. To see onto, what do we do is that given a matrix here, does there exist? So this is an algebra isomorphism. And fourth thing is that this is one to one. This map is one to one. That you can prove easily using the property of the basis vectors VLs. So what we get here is that this is an isomorphism, algebra isomorphism of AFV into MNF. Now this map is onto poles. That can be easily seen. This map is onto, can be seen as follows. So for any matrix, let us say A, with entries say alpha ij, n by n, what does it mean? This is the matrix. No? Alpha 1, 1, alpha 1, 2, alpha 1, n, alpha I1, alpha I2, and this is alpha In. Alpha n1, alpha n2, alpha n by n. And somewhere here is your alpha 1j, alpha ij, alpha n, and j. So this is what it is. Good. So for a matrix here in MNF, to show that there is a linear transformation, say T. Now define this T, V to say V, every vector V here, this can be written as a linear combination of, let us take V to be specific, say Fn, then things will be even better. So let us take this V to be Fn. Let us take V to be Fn. So Fn means this is F cross F cross F n times, and therefore every entry here would be an n tuple. Let us take x1, x2, and this is xn. And Vt is what? Vt is the product of the matrices. So this product of the matrix here you can take. So this is x1, x2, xn, and the matrix A. So this is 1 by n, this is n by n. Right? A. This is 1 by n, this is n by n. So the product is 1 by n. Now you can see that what you get here is this x1, x2, xn. How to determine this linear transformation? If we know the effect on the basis vectors. So what is the VIT? So let us take the standard basis say B for the this V is equal to Fn. The standard basis is V1, V2, Vn. So this V therefore is x1, x2, xn. This is same as x1, 1, 0, 0, 0, xn, 0, 0, 0, 1. So this is same as x1, v1 plus x2, v2, xn, vn. So this is what it is, so VIT. So if V is this, then VT can be determined. So for every V, VT can be determined by knowing VIT. What is VIT here? So VIT is, so you can take 0, 0, 0, 1, 0, 0, 0. This is ith position. And A. So if you multiply this with A, and A is this alpha 1, 1, alpha 1, 2, and so on and so forth, then you can see that this entry here, this product, that will give you, right? Multiply, and this will give you alpha I 1 and E11, EI1, V8. This is V, this is here is F. So this is alpha I1, then you have alpha I2, alpha In. So this is the ith row here of A. And this is an element here in Fn. So T is a map Fn to Fn, and this linear transformation can be determined by knowing VIT. So this can be considered therefore T as the linear transformation by defining the map VIT means this is VIA. And what is VIA? VIA is the product of two matrices where one matrix is VI of order 1 by n and the entries of VI are all zeros except on the ith place, which is 1. When you multiply this with A, you get just ith row of A, namely alpha I1, alpha I2, alpha In. So T is a linear transformation. If you define VIT to be like this, so T is a linear transformation here in V, where V is Fn over F. If you define, say, VIT as just now, here the ith row, alpha I1 and this is alpha In. Here. Then this is a linear transformation that can be determined using this. And you can see that this is the linear combination. So alpha I1, x1, alpha I2, x2. So what is the linear transformation here T? That is obtained using the multiplication VA. So this is the linear transformation. T is the linear transformation therefore VA. Now this VA is actually product. So you can treat that this A as a linear transformation. This you can write as VA. So how are we defining V under A? As the product of two matrices V of order 1 by n and the matrix A of order n by n. Now T is a linear transformation, so the map has become onto. So what we have proved is this theorem that the set of all n by n matrices over a field F is an associative algebra. We denoted this by M and F over F, and the dimension of this is n square. On the other hand, we already have one associative algebra with identity of the same dimension, namely n square over F. This theorem says that these two algebras are isomorphic, and one such isomorphism is obtained using an ordered basis, say B, V1, V2, Vn, for V over F. And how the map is defined? The map is defined, say M. So it sends every linear transformation T from AFB to M and F. And the image of T under this map is the matrix of T with respect to the ordered basis P for V over F. So this is what we have obtained so far. So I think we have to wind up here. We shall then next time see more of this MNF. Till then, thank you very much for your kind attention. We shall meet then now on Tuesday. Thank you very much.
Thank you, sir.